Hi, everyone, and welcome to week 3 of your online learning. Today, we're going to finish our thermal portion of this unit by talking about thermodynamics. More specifically, if a reaction can be thermodynamically favorable or unfavorable. So it says thermodynamically favorable reactions are those reactions that occur without aid. Thermodynamically unfavorable reactions are those reactions that do not occur without aid. While enthalpy is important in determining this, there are also other things to take into consideration. So when we talk about if a reaction is thermodynamically favorable or unfavorable, it just means, will this occur by itself? Do I have to do something to it? One of the things that goes into a reaction being thermodynamically favorable, of course, is our delta H, which we know is our enthalpy. But another thing that goes into it is something called entropy, which we have a capital S there. It's the amount of chaos or disorder. Very important, just like enthalpy with our signs, our delta S's with our signs are important. When delta S is positive, it becomes more chaotic. Delta S is negative, it becomes less chaotic. The universe tends to become more chaotic just in general, so things are almost always a positive delta S. And we can find delta S just like we did with delta H, the sum of the S of the products minus the sum of the S of the reactants. So it says a solid to a liquid to a gas, an increase in heat, an increase in the number of particles, an increase in complexity of the molecule, all increases the chaos. Think about what's happening at the molecular level. Is it moving faster? Is there more of it? Those things would lead to more chaos. So here we want to calculate the enthalpy. No, that should say entropy. Entropy for nitrogen given the following information. So I've got the total right here. I've got all of the information for everything else, so I'm just going to plug it in just like I would the other ones. So we start with positive 605.9. Pay attention to these units here. It's joules per moles times Kelvin. All of the units are the same, but when we look forward, delta S is always in joules for the most part, and delta H is almost always in kilojoules, so that's something you want to pay attention to, is equal to, so the products would be N2, which we don't know, plus, we got 4 water vapors, 4 times 188.7. And then subtract from the reactants. The reactants are going to be the N2H4, so that's 121.2, plus, I got 2 hydrogen peroxides, 2 times 109.6. You go ahead and you do that math. Everyone should be working on this, doing it to make sure that they can get the answer of 191.5. And again, joules per moles times Kelvin. Okay, pretty simple. Again, in this unit, you're basically doing the same thing for different things. So enthalpy, entropy, all found the same way. And there's multiple ways to solve it. Okay, so a reaction will always be thermodynamically favorable if it is exothermic and increasing in chaos. So that means my delta H is negative and my delta S is positive. That will always be favorable. And it will always be unfavorable if my delta H is positive and my delta S is negative. So for other situations, it will depend upon the temperature. And we can calculate Gibbs free energy, which is a delta G, in order to determine if a reaction will be thermodynamically favorable or unfavorable. You can get a number, a value for it, which sometimes is whatever, but typically it's just that sign that will tell us if we are favorable or unfavorable. And again, those signs are very important. So when delta G is positive, it's unfavorable. Delta G is negative, it is favorable. And so this is where we have to pay attention to our units. So delta H is in kilojoules, delta S here is in joules. So before I even do anything, I'm going to change this negative 285 joules. That's really, it doesn't really matter about the other ones. And that's going to be, I'll just write it out. The same as negative 0.285 kilojoules per moles times Kelvin. Okay. So you'll see in this temperature is in Kelvin. So I'm going to take my 25 degrees Celsius plus 273, and that will give me my temperature of 298 Kelvin. So now I've got my temperature, I've got my delta S, I've got my delta H, they're all in the same units, and then I can plug it into my equation. Delta G equals delta H minus T delta S. So delta G equals, let's see, 196 kilojoules per mole minus the temperature 298 Kelvin times negative 0.285 kilojoules per moles times Kelvin. When you do this, it's going to be 281 units kilojoules per mole. A lot of the times you'll see per mole of RXN, so that's just saying per mole of the reaction. And so then to answer the question, will it be spontaneous or not? So will it be thermodynamically favorable or not? So this would be unfavorable. So it does not occur without aid. So it needs some help in order for the reaction to actually occur. And that's how you would do Gibbs free energy to determine if it will be thermodynamically favorable or unfavorable. And with a question like this, you want to make sure, okay, I've got this number, but I haven't technically answered the question until I write that it is unfavorable. Okay, and then the last page for today, this gives us the rest of our thermo portion, and we'll start with the kinetics part next week. Just another way to calculate delta H. There are so many ways to calculate delta H, and this way we can do it with bond energies. So bond energy is the energy needed to break the bonds in 1 mole of a gas into gaseous products. This is yet another way to determine the enthalpy for a reaction. So this one is different because it's bonds broken minus bonds formed. Bonds broken, those are the reactants, minus the products. And everything else that we've seen has been products minus reactants. So you want to keep that in mind. Keep in mind that it always requires energy to break the bonds, and energy is released when forming bonds. Whether a reaction is endothermic or exothermic just depends on which is larger. So the example says use the bond energies to estimate the enthalpy for this reaction. So what you really need to do when you do this is draw out the structures so that you can see how many of what type of bond you have. So C2H4 should be a double bond, carbon, 2 hydrogens on each. You know what water is. C2H5OH is ethanol. Okay, so now we have all of our bonds. There are my reactants. So the reactants, I have a C double bond C, which is 602 units kilojoules per mole, plus I've got 4 CH bonds, 4 times 4, 13, plus I've got 2 OH bonds, which is 463, and that should be all of the reactants, okay, minus the bonds that are formed, which are the products. I've got 1, 2, 3, 4, 5 CH bonds. I've got 1 CC bond. I've got 1 CO bond. And then I have one OH bond. Okay. When you do that math, that should give you negative 52 kilojoules per mole. And so you could go through and be like, okay, so that's my delta H. It's an exothermic reaction. And that's just another way to calculate delta H. So please look at the assignments that are for this week. Please let me know if you have any questions, and please make sure you keep sending me your work so that I know you are actually doing something. All right, have a great week.